All right, today's lesson video is going to be about gas laws. So, today in class we talked about how gas laws usually are going to use a volume that's in liters, and of course we could have milliliters or liters. It's very unusual to see a gas law problem that is done in gallons or some other volume. So, when we're talking about gas volume, samples of gases are compressible. There's a large amount of empty space between the gas particles. Gases do not have a strict volume. They expand or spread out to take the shape and the volume of their container. If the volume of the container increases, the volume of the gas expands to fill it. So in our pictures here, it's just showing the gases being compressed or the volume being expanded, and the gases will move and spread out to fill the space. One thing to note is when we're drawing particles of gases, we tend to draw them as little circles. The problem with doing this is that it really doesn't give you a very accurate picture of what the spacing is between particles. These gas particles or gas molecules are very, very, very small. The space between them is very, very, very large. So when we draw these things, it looks like, hey, they look pretty packed together, but that's really not the case. They're not going to be very packed together unless we take things down to a low temperature and then really give them a tiny space for the amount of particles that we have. So let's go ahead and talk about temperature. So gas is always going to be measured in Kelvin. So whenever we're doing any kind of gas law problem, we want to convert Celsius to Kelvin. Remember, to convert Celsius to Kelvin, you're going to take your degrees Celsius, and then you're going to add 273.15, and that will give you your temperature in Kelvin. So temperature, if we increase the temperature, you can see that our arrows are now longer, which means the speed of our particles is now faster. Gas particles are in constant motion, and each gas particle has something called kinetic energy. This is the energy of motion, or the energy of movement. So the particle's kinetic energy is related to its speed and its mass. As gas particles heat up, their speed increases. As gas particles cool, their speed decreases. Gas pressure is often measured in atmospheres. We've also used kPa, psi, and torr as gas pressures units. Gas particles are constantly in motion and often collide with each other and the walls of their container. The pressure of a gas is the force that the gas exerts on the walls of the container. When you fill a balloon with air, the balloon expands because the pressure of the air molecules inside the balloon is greater than the pressure of the air outside the balloon. When you stop filling the balloon reaches a particular size where the pressure inside equals the pressure outside. So looking at our example here we have inside the balloon, and this is outside the balloon. When the pressure inside equals the pressure outside, the balloon is going to stop expanding. If we do something so we increase either the speed of the molecules or we add more molecules, it's going to cause this balloon to actually expand and get larger until finally the pressure outside equals the pressure inside. So continuing with the kinetic theory of gases, gas particles have a very small or insignificant volume compared to the volume of the space between particles. Again, these particles are very, very, very tiny, and they're spread out very, very far. The second thing about kinetic theory of gases is that particle non-attraction, that gas particles exert no attractive force on each other or the container walls. They do not attract or repel each other. So when we're thinking about what is correct and what is not correct, when a gas particle is flying around inside the container and it strikes the wall of the container, it's going to bounce off and continue on till it strikes something else. Gas particles do not hit the walls of the container and then just stick. So this would be, they just keep bouncing. Off of each other and any other thing that's in the container. Number 3, particle motion. Gas particles are in constant motion. And always move in straight lines. Until they collide into another particle or the container wall. Looking at our picture here, you can see that they're moving in a straight direction. They do not twist and turn and move around. Number 4, particle collisions. Particle collisions are what we call elastic. The kinetic energy of each particle is conserved as they bounce off of each other or the walls of the container. They do not lose energy when they collide. The average speed stays the same. So if we have two particles that are going at the same speed and they hit, they're going to bounce off and travel off at the same speed. They don't lose speed at all. This would be incorrect. We have two particles traveling at the same speed. They hit, and then they slow down because they hit. That is not true. Nope. They just keep bouncing off of each other. Number 5. Average kinetic energy. The average kinetic energy of a gas particles is directly proportional to the temperature only. If the temperature drops to absolute 0, the particles stop moving. So any temperature that's greater than 0 degrees Kelvin, we're going to have particle movement. A temperature equal to 0 degrees Kelvin, it's going to have no movement at all. And we talked in class about how this has not yet been achieved. A gas that follows these rules is a theoretical gas called an ideal gas. Under usual conditions of standard temperature and pressure, most real gases are going to behave just like their ideal gases. So let's talk a little bit about ideal gases. To create a law that accounts for all of the others, a scientist, Émile Caprion, in 1834 came up with the ideal gas law. This equation is also called the general gas law. Again, to recap the following principles, the kinetic energy, the volume of each particle is insignificant when compared to the volume of the container. All collisions are elastic. No force of attraction exists between particles or between the particle and the container. So in the ideal gas law, which we did in the big packet, R is the constant. It's the same for all hypothetical ideal gases. Remember, we can have different units. We can have different types of pressures. But the thing with the ideal gas law, it's also known as the Picky law. All units must match these units. So if you're using this particular constant and your volume is in milliliters, you're going to have to convert that to liters. If you're doing this gas using this constant and you're given the grams of a certain gas, you're going to have to convert that to moles. And of course, whenever you're doing a gas law problem and you're given Celsius, you've got to convert that to Kelvin. So the same symbols that we've been using all along, the V will stand for volume, P stands for pressure, the N is the number of moles or number of particles, R is that constant, and T is temperature. So let's work out one of these problems. If a scientist has a sample of ammonia with a volume of 2.15 liters at standard temperature and pressure, and it tells you what standard temperature and pressure is, how many moles of methane are in that sample? So you can see that there's no change here. This is one set of conditions. So we're going to have volume. Our volume is 2.15 liters. Our temperature is 0.00 degrees Celsius. I'm going to go ahead and convert that to Kelvin right now. My pressure is atmospheres, and that's going to be 1.00 atmospheres. N is my unknown, and my R value is written up above, and that's 0.08206, and that's going to have that weird unit, which is liters per atmosphere per moles per degree Kelvin. The formula I'm going to use is PV equals nRT. In this case, the N is my unknown, so I need to get it by itself and isolate my variable, which means I need to get rid of the R and the T. So I'm going to divide them by themselves to get rid of them. If I do it to that side, I'm going to need to do it to this side, which means the formula that I'm going to substitute it into is PV divided by R times T will equal N. So N equals, now I'm just going to substitute in the numbers. My pressure was 1.00 atmospheres. My volume is 2.15 liters. The R constant is 0.08206 liters, atmospheres, moles, degree Kelvin. And my temperature, after I converted it, is 273. So when I put that in the calculator, N is going to equal, and I'm going to use my fraction button, N is going to equal 0.095971, and so on and so forth. Now let me check my significant figures. I'm going to look at my problem. I've got 3 here, 3 here, and 3 here, so I'm going to need 3 significant figures for my answer. Decimals present, so here's my first one, my second one, and my third one. The 9 is followed by a 7, so that's going to cause the 9 to round up. That becomes 10. Carry the 1. So when I convert this number, this is going to be equal to 0.0960, and our unit is going to be moles. I've got my 3 significant figures. This particular sheet we can cross right off. We're not going to deal with density. All right, here's our next one. If the temperature and the amount of gas in a container are held constant, the pressure of an ideal gas will be inversely proportional to the volume of the container. So as the volume shrinks, particles collide with the container walls more often, and then the pressure will increase. As you can see, pressure is going to be inversely proportional to volume. Here's another way to write the equation. Of course, P equals pressure. V is volume. And then K would be a constant. So this following equation down below here can be used to calculate the pressure or volume of a new state. Remember, we've got change going on here, as long as the temperature and the number of particles remains the same. So here we have our formula. Now, each time you're rearranging this, you've got to isolate the variable. It doesn't matter which of these formulas you're using. We're just going to use some algebra to solve this. So let's say that the pressure is our unknown. In order to isolate the variable, I'm going to need to divide V2 by itself to get rid of it on that side. If I do it on that side, I'm going to need to do it to the other side as well, which means that now the second pressure is by itself, and I'm ready to work that type of formula. So let me go ahead and erase this, and we'll work out this next problem. This is Boyle's law. So, a scientist has 2 containers. Container A is empty, and I like to write on these, and it has a volume of 25.0 milliliters. Container B contains an ideal gas at a pressure of 1.50 atmospheres, and it has a volume of 25.0 milliliters. So that's my initial condition. The scientist connects the 2 containers using a 5 milliliter tube. What's the new pressure throughout the system? Let's go with our initial conditions. So my volume, well, I only have gas in this container, so the volume of gas is 25.0 milliliters. The pressure, it tells us when we're reading the problem, is 1.50 atmospheres. Now let's go for the ending condition. That's these right here. Well, now I can see that I've got gas in this container, and I also have it filling the coil. The coil is 5 milliliters. Vial A is 25. Oops, let me change that. 25.0 milliliters. And vial B was also 25.0 milliliters. So when I add 25 plus 5 plus 25 more, I'm going to get a total of 55.0 milliliters. That's my total volume. So that's going to go right here. And then pressure 2, reading my problem, what is the new pressure throughout the system, is going to be my unknown. So now I'm going to rearrange my formula. Well, P2 is my unknown just by accident. So I'm going to need to isolate it, divide V2 by itself, and that disappears. If I do it on that side, I'm going to need to do it on this side. And now I'm ready to substitute in my numbers. So my pressure 1 was 1.50 atmospheres. times my volume 1, which was 25.0 milliliters, over my volume 2, which was 55.0 milliliters. And that's going to be equal to my second pressure. So put it in the calculator. And P2 is equal to 0.681. I need 3 significant figures, and that's going to be 0.381, and that's going to be atmospheres. And there you have it. Thank you. Thank you very much.